Welcome to a lecture on mechanical properties of solids for Bsc VI students in 6.2 paper of their syllabus by Miss A. Shirley Jones, Associate Professor and Head of the Department of Physics of V.V. Sanga's Veerashaiva College, Ballari. In this chapter of mechanical properties of solids, we are going to concentrate and study a few properties, mechanical properties like strength, elasticity, hardness, fatigue, creep, and fracture. Now, what are mechanical properties? First, let us see what is a property. The term property is a qualitative or quantitative measure of response of materials to extremely imposed conditions like forces and temperatures. Materials have various kinds of properties. The properties of materials are classified into chemical properties, physical properties, mechanical properties, and dimensional properties. As a physics student, in the beginning, we have seen what are physical properties of materials. Elementarily, our physics study starts with knowing its mass, charge, density, effect of electric field, effect of magnetic field, and later we see what are the thermal properties, electrical properties, magnetic properties. Like that we go on studying. But what are these mechanical properties? Now, mechanical properties of the material are the behavior of the materials under applied forces. Now, they are usually related with elastic and plastic behavior of the material. Of course, Hooke's law is also connected with this. These properties are expressed as functions of stress and strain, and of course the famous Hooke's law. A sound knowledge of the mechanical properties of materials provides a basis of predicting the behavior of the materials under the action of different forces or loads and designing the materials to form the components out of them. Now, the various mechanical properties of materials are strength, stiffness, elasticity, ductility, malleability, brittleness, hardness, machinability, resilience, toughness, creep, brittleness, fatigue, and fracture. We're not going to see all the properties, but we are going to concentrate in this lecture few of the mechanical properties like strength, then ductility, then fracture, creep, and brittleness, and of course the elementary property what we have already seen in Bsc first semester or first year, that is elasticity. Now first let us know about strength. What is strength of a material? Strength of the material is the capacity of the material to withstand destruction under the action of external forces or application of loads. The stronger the material, the greater is the force it can withstand. Therefore, the strength of the material determines the ability to withstand stress without any breakage or failure. Now, the strength of the material varies according to the type of force. Now, the three kinds of application of forces are tensile loading, compressive loading, and shearing or torsional loading. Now, what is tensile loading? Since the tensile loading produces elongation, The strength of the material must depend on the Young's modulus of the material. Now, Young's modulus, bulk modulus, rigidity modulus are the coefficient or the moduli of elasticity a material has by the application of the external forces in three different ways. In tensile loading, there is an elongation. In compressive loading, the strength of the material must also depend on the bulk modulus of the material. In shearing and or torsional loading, here it depends upon the shear modulus of the material. First, let us see what is this elasticity. Elasticity is the property by virtue of which a material regains its original state after the removal of the deforming force acting on it. Now, the recoverable nature of the material is called as the elastic property, and the elastic deformation makes it possible to store energy in solids and then release it under the control conditions. This is a beautiful property which is exhibited by all the materials. Elasticity of solid has its origin in the existence of interatomic or intermolecular bonding, which we have seen in the last chapter. Now, in order to understand elasticity, we need to know two terms. One is stress, another one is strain. Well, what is stress? The internal restoring force per unit area of the body to keep the body in equilibrium under the action of deforming force is called as stress. Now, there are two kinds of stresses. One is called as normal stress and the other one is tangential stress. Well, what is normal stress? Normal stress is the force acting per unit normal area, and it tends to change only the size of the body. However, the tangential stress is the force per unit area and is changing both size and shape of the body. Now, however, the general formula is stress is given by force per area, and stress has got dimensions m, l minus 1, t minus 2. Now let us see what is strain. Strain is the ratio of the change in dimension of the body by the application of deforming force to the original dimension of the body. It has no dimension because it is change in, for example, length to the original length. So it has no dimensions. Now, strain is also of three types. One is linear or longitudinal strain, which is nothing but the ratio of increase in length to the original length, that is dl by capital L. Second one is the volume strain. It is the ratio of increase in volume to the original volume, which is dV by capital V. And the third one is the shearing strain, which is the angle of shear theta and is measured in radians. Now let us see the famous Hooke's law, which can be stated as within the elastic limit of the material of the body, the stress is directly proportional to strain, or stress by strain is a constant called as modulus of elasticity. There are three kinds of elasticity. They are Young's modulus, denoted by the letter Y, which is equal to normal stress by linear strain, that is F by A divided by strain, small l by capital L, that is change in length to original length, and we have got F into capital L divided by A into L. Second one, bulk modulus. It is the ratio of normal stress to volume strain, which is obtained as pressure into volume divided by change in volume. Now, the rigidity modulus, which is the ratio of tangential stress to shearing strain, which is F by A divided by theta. Now there is another important parameter called as elastic limit. Every body has got, every material or every solid has got elastic limit. Now what is this? When a load is applied to a wire, its length is gradually increased. Initially, strain increases linearly in accordance with Hooke's law, and further increase in load leads to random variation and ceases to follow Hooke's law, as shown in the graph of the stress versus strain. Now let's study this graph. The maximum stress up to which the body exhibits elasticity and obeys Hooke's law is called as elastic limit. All materials have got elastic property and every material has got an elastic limit. Now this is shown by the part OA in the curve. Now, the stress corresponding to point B at which a large increase in strain commences is called as yielding stress. Second point, if the load is removed at yielding stress, the wire is left with a certain amount of strain called residual strain, represented by OC in the graph. Now, the third point is the yielding stops at D, and on further extension, material becomes plastic and it can be produced by gradual increase in the load. The part D represents the plastic ring. On further increase in the applied load, the wire finally breaks at the point E, and the point E is called as breaking point. Now let us understand what we mean by the second parameter we are going to study, that is hardness. Now what is hardness? Hardness of a material measures the resistance of the material to various kinds of permanent shape changing due to compressive force applied. Now hardness is the measure of the permanent change in shape due to the application of loads. That means it is the resistance developed within the material to permanent shape changing forces which are applied. Now the macroscopic hardness is characterized by the strong intermolecular bonds. That means this resistance comes out of the strong intermolecular bonds which exist within the material. The behavior of solid materials is very complex under action of force. Hardness increases with the decrease in particle size. That means smaller the size, greater is the hardness. This is known as Hall patch effect. However, below a critical grain size, hardness decreases with the decreasing in grain size. This is known as inverse Hall patch effect. Now the common examples of hard matter are, of course, your ceramics, concrete, certain metals and super hard materials. How to measure the hardness? Now there are mainly three types of hardness measurements. They are scratch hardness measurement, indentation hardness measurement and rebound hardness measurement. Well, what is scratch hardness measurement? Now, scratch hardness measurement gives a measure of how resistant the material is for fracture or permanent plastic deformation. Now, this is due to friction from sharp objects. That means when a sharp object is on a material or scratched on a material, there is for a fracture can occur or a permanent plastic deformation also take place in that material. Now the principle of measurement is that an object made of harder material will scratch an object of softer material. Now diamond can easily scratch or even cut. This type of hardness measurement is useful while testing the hardness of thin coating on materials. Hardness in that case refers to the force necessary to cut through the film on the substrate of the material. Now, let us come to the second hardness measurement, that is indentation hardness. Now, indentation hardness measures the resistance of a sample to material deformation due to constant compression load from a sharp object. Now, the first one, that is scratch, is the resistance offered for a sharp material incident on it. But here the material offers resistance for a constant compression by a load or a sharp object. That is the second type of hardness measurement. Indentation hardness measurements quantify the resistance of a material to plastic deformation. It is divided into two classes: micro indentation tests. These tests have forces less than 2 newtons, and the second one is the macro indentation test. These tests have forces more than 2 newtons. Now, it is to be noted that hardness is not considered to be a fundamental material property. Instead, it represents an arbitrary quantity used to provide relative idea of material properties. Now let us know about the third kind of hardness, that is the rebound hardness. Now, rebound hardness is also known as dynamic hardness. Now, what does it measure? It measures the height of the bounce of a diamond-tipped hammer dropped from a fixed height on a material. Now, you know that when material falls sharp on another material, they bounce back. The material which produces more height during bouncing of hammer is considered to be more harder. Now, this measurement of hardness is measured in moles because it is the resistance offered per. So, mos is the unit, and the materials in the order of increasing hardness are measured in the following table, and it is given like that. Now, mos hardness is numbered as 1, 2, 3 like that, and the mineral names are given and the chemical formula are given. It is to be noted that the absolute hardness of talc is 1, while diamond is 1600, which is the most hardest material which is found. And of course, these crystals, calcite and quartz, topaz, all these come in this list in the order shown. Now, there is another table which shows the hardness of different materials. Graphite hardness in mos is given between 1 and 2, while chromium is 8.5. Now we have got gold, you see, 2.5, and silver 2.5, copper 2.5 to 3, and these are the materials, their hardness. They are taken in order to melt, in order to mold, in order to design. Now let us understand what is called as fatigue. Unlike the fatigueness which we get, humans get, even materials have the property called as fatigue. What is fatigue of a material? Fatigue is the weakening of a material caused by repeatedly applied forces or loads. It is considered as the progressive and localized structural damage that develops within the material when a material is subjected to cyclic loading. Mind you, it is not simply loading, it is cyclic loading. That means on and on and on. Now, the nominal stress values that cause such damage may be much less than the ultimate tensile stress limit, that is yielding stress limit. Now, when the failure of the material occurs due to continuous cyclic loading, then the material is said to have poor or no fatigue strength. Fatigue occurs in materials used in machine components subjected to continuously to cyclic forces or loading, such as motor shafts, bolts, springs, gear teeth, valves, turbine blades, aeroplane parts, automobile and gas engine parts, etc., etc., which also includes suspension bridges, wire ropes and many other machinery parts. So, now this factor, fatigue, must be measured, known for a material, and how it can be, avoided. And we have to use the materials, keeping the conscious that the materials has fatigue property. Now, 80 to 90% of total failure of high-speed machine parts is due to fatigue in industries. Now let us understand the mechanism of fatigue failure in materials. Fatigue failure begins at irregularities on the surface of the material first, which acts as a stress raiser and point of high stress concentration. This is the first thing which happens. Next, the basic mechanism of fatigue is slip. Now, we try to experience it next. Some crystals in the stress region of metal reach their limit of elastic action sooner or later owing to their unfavorable orientation, which permits a slip to occur. Now, what do you mean by this? The elastic action stops in some crystals due to stress points or concentrated stress points. When the piece is subjected to cyclic stress variation, the constituent particles tend to move slightly with respect to one another. That means inside there is a little movement. This movement finally weakens some minute element to such an extent that it ruptures, and microscopic cracks or series of cracks originates on the surface of the piece. So cracks are the symbols telling that the materials have got fatigued. In such zone of failure, a stress concentration develops, and with successive repetition of stress, the fracture spreads inward from this nucleus across the entire cross section of the material. Ultimately, finally, the affected part of the section is reduced to a small core, no longer capable of sustaining the applied load, and the specimen breaks into two parts. Now let us see what are the factors affecting fatigue strength. They are the chemical composition, that's the first one. Next is grain size in the crystalline structure, amount of cold working, temperature, surface conditions. Among these, surface conditions are very important as erosion and corrosivity comes here. Now, surface conditions affect fatigue strength in three ways. Through the geometry of the surface, that means the surface roughness, the surface's porosity, and foreign inclusions like slag, oxide, oxidation. These are the characteristic geometrical and physical defects of the metallic surface. That's the first one. Through the physical nature of the surface layers also, the cracks, the damage and all. Now the third one is through corrosion due to environment. The main effect of the corrosion is to produce sharp pits from which numerous cracks form, frequently meeting to form the serrated fracture. Now, how to tackle with this fatigue? Now design, there is a design. Now to produce satisfactory fatigue life, it is necessary to observe the following points in designing procedure of materials. Modification of the design to avoid stress concentration by eliminating sharp recesses and severe stress razor. Now, the machinery should be designed in such a way, in its shape, and such that stress concentration points should be eliminated. Now, precise control of the surface finish by avoiding damage to the surface by rough machining, punching, stamping, shading, etc. can be done. Now, the third point is control of corrosion and erosion, or chemical attach in service, and prevention of the surface during processing or heat treatment. Now I told you that the material's response is different for first the loads or the forces, and the thing is, another one is temperature. Now corrosion is very important, and we need to know how to tackle with corrosion. Now the surface treatment of the metal, since fatigue is essentially a surface initiated phenomenon, the conditions of the surface is particularly important. Also, since fatigue occurs by slip, any structural condition that can inhibit slip would be useful for long fatigue life. Now let us see the other important mechanical property called as creep. Now what is creep? Now creep is the slow and progressive deformation of a material with time at constant stress or higher temperatures. The simplest type of creep deformation is viscous flow. Now, once the creep sets in, it continues until the sufficient strain has occurred so that a necking down and a reduction in cross-sectional area will occur. Now, I said that it is a deformation of the material with time. So, the important factor here is the time, and as time goes on, there is a progressive deformation under the application of constant stress or changes in temperature. Creep is observed in all types of materials, that includes metals, ionic and covalent crystals, and amorphous materials too, such as glasses and polymers. Metals, ionic and covalent materials exhibit creep at high temperature, whereas plastics, rubber and amorphous materials exhibit creep at lower temperature scale. They are very sensitive to this temperature. Now there are three kinds of creep based on how the creep varies at different temperatures for a given load. That means we have a constant stress, that is application of load or force, and at this constant load and at different temperatures we have three kinds of creep. First one is logarithmic creep, second is recovery creep, third one is diffusion creep. Well, what is logarithmic creep? At low temperatures, the creep rate decreases with time, and the creep in this region. The creep rate in this region decreases with time, and creep curve is logarithmic in this region. Very simple, direct. Now the second one is the recovery creep. In the range of temperature between 0.5 Tm to 0.7 Tm in Kelvin. Okay. The influence of work hardening is weakened, and there is a possibility of mechanical recovery. Due to this, the creep rate does not decrease as rapidly as at low temperature. So what happens at very low temperature? The hardening is weakened, and there is a possibility of mechanical recovery. That means deformation. It doesn't occur. Now the third one is diffusion creep. At very high temperature beyond 0.7 atm in Kelvin, the creep is primarily influenced by diffusion and the stress applied has little effect. The creep may be therefore be classified as primary creep, secondary creep and tertiary creep. Now there is a graph which shows the creep curve at different stages of creep. Creep curve is a graph showing the variation of extension, that is strain of a material with the time under a definite normal stress and constant temperature. Creep curves show the following stages. Now the primary creep in the creep curve represents a region of decreasing creep rate. It is period of predominantly transient creep in which the creep resistance of a material increases with time. Just remember, the creep increases with time. The secondary creep, it is a region in the creep curve in which the creep rate is nearly constant. So in the secondary, constant with time. In the third tertiary creep, there is a third stage of creep. In this region, the creep rate increases and hence creep accelerated linear curve. In this region, it represents a region of progressive damage resulting in an imminent fracture of the material occurring through intercrystalline planes. Now, what are the factors which affect creep? First, grain size. Now, it takes a major role in creep mechanism. Generally, coarse grain materials exhibit better creep resistance than fine grain materials. That's why concrete, you see, has got the best size. This is due to the fact that fine grain materials have greater amount of grain boundary, and the grain boundary behaves as a quasi-viscous material with a high tendency to flow at elevated temperature. The second point which affects creep is the thermal stability of microstructure of alloys and its resistance due to oxidation at high temperature. Third one is prior cold working also has a strong effect on creep, which is accelerated in some metals during recrystallization following cold work. This accelerated creep is followed by a period of relatively slow creep in the recrystallized metal. Now this one is slow creep when turning back. Now the fourth one is pure metals which have high melting points and a compact atomic structure generally exhibit good creep resistance at high temperature. Now the creep resistance of pure metals can be increased by alloying them with suitable elements. Now how does creep occur or creep is happening? Let us understand the mechanism of creep. It is related to the movements of dislocation. At low temperatures, strain is restricted. As a movement of dislocation is stopped by grain boundaries or by impurity atoms when at low temperature. However, at high temperature, atomic movements permit the dislocation to climb. It jogs out of its plane of slip or even by annihilating. The vacancies and atoms move to and from the dislocation. The dislocation climb out the initial slip plane, thus permitting the continuation of incremental stress or creep. The climb is ascribed to the thermal agitation of surrounding atoms. In addition to this, the grain boundaries also acquire greater mobility and undergo changes which in turn influence the rate and the nature of creep. First, we have seen that at low temperature, the movement of dislocation is almost stopped. Second, at higher temperature, it creeps between the spaces between the atoms and the dislocations. Next is the vacancies. Next is due to the thermal agitation. Now, the grain boundary resists the creep at low temperatures while it assists the deformation at higher temperature. The temperature at which the strength of the grains and the grain boundaries is equal is called as equicohesive temperature. We have seen creep, we have seen hardness, we have seen fatigue, and we will see brittleness. Now, how to remember all these things? Let us review back and know these properties in a simpler way. Well, what is that? Hardness is the property of the material which avoid indentation or penetration or scratching. A material is hard if it doesn't allow scratching. Next is fatigue. It is the failure of the material under repeated and reversal application of load or forces. Creep is slow and progressive deformation of the material under constant load and temperature. Creep has two parameters to depend on, that is load and temperature. Fatigue only on repeated load. Now the brittleness will come, that is immediate failure of materials without any permanent deformation, which happens in glass. Now let us understand what is fracture. Now everybody gets a sense by the physical literal meaning of fracture, but fracture is the separation of an object or material into two or more pieces under the action of stress. In simple, that means when it breaks, when it has a fracture. The fracture of a solid usually occurs due to the development of certain displacement discontinuity surfaces within the solid. If the displacement develops perpendicular to the surface of displacement, it is called normal tensile crack or simply a crack. If a displacement develops tangential to the surface of displacement, it is called shear crack or slip band or dislocation. Now this fracture, we measure this parameter with what is called as fracture strength. It is also known as the breaking strength, and it is the stress at which the specimen fails via fracture. This is usually determined for a specimen by a tensile test which charts the stress strain curve as shown in the graph. In the graph, the final recorded point is the fracture strength. Now there is a yield point, there is an elastic limit, there is a proportional limit, and the rupture strength, ultimate strength, and actual rupture strength. Now we should note a few points here. The ductile materials. What is ductile material? Or which ductile materials are the ductility is a property shown by materials which enables the material to draw into thin wires. That is ductile property. Now ductile materials have fracture strength lower than the ultimate tensile strength. This is due to the reason that in a load control situation it will continue to deform with no additional load application until it ruptures. Whereas brittle materials have fracture strength same as the ultimate tensile strength. In this case the fracture is sudden and occurs at. Now there are two kinds of fracture. One is brittle fracture and the other one is ductile fracture. Now what is brittle fracture? Now brittle fracture, in this type no plastic deformation occurs before fracture takes place. That means you cannot know suddenly it becomes brittle. No sign of plastic deformation. Second, in this case the fracture can occur by cleavage as a result of tensile stress acting normal to crystallographic planes with low bonding cleavage planes. In amorphous solids, the lack of crystalline structure results in a conchoidal fracture with cracks proceeding normal to the applied tension. Now, brittle fracture may be avoided by limiting pressure and temperature within limits. Now, a substance or a material goes brittle when we vary the pressure and temperature. Brittle fracture prevention curve defined by weakest components at given temperature and pressures, allowing for largest undetected pre-existing flaw in each component. Now, ductile fracture. In this case, plastic deformation takes place before fracture occurs. In ductile fracture, there is slow propagation and an absorption of large amount of energy before fracture occurs. Basic steps involved in ductile fracture are void formation, void coalescence, that is crack formation, crack propagation and failure. All this together result in a cup and a cone-shaped failure surface, that is ductile fracture. Let us see basically what are the differences between ductile fracture and brittle fracture in short. In ductile fracture, excessive plasticity. In brittle fracture, there is no deformation, permanent deformation or little plastic nature. Okay, excessive plastic deformation occurs until the fracture occurs in ductile fracture. Now, the second basic difference is dull fracture surface we have in ductile fracture, but in brittle fracture, bright and shiny fracture surfaces are found. Now, in ductile fracture, stable crack propagation, and in brittle fracture, it is unstable crack propagation, and it continues, leading the catastrophic crack propagation and failure. Now, in ductile fracture, cup and cone type fracture surfaces appear. Now, in brittle fracture, it is brittle, it will be grainy, it is grainy faceted fracture, surface will appear at the crack. Now, these are some of the mechanical properties. We have seen only few, but there are various other properties which I have mentioned earlier must be considered in order to use materials for a definite purpose. Now, these ideas are given in physics, but they are engineered by the engineers in order to form the machinery with perfect, which can be used for a longer time, longer sustainability, avoiding all the defaults, that is application of forces on and on, the loads I mean, and of course the variation of temperatures and the variations in chemical compositions which affect them. So all these factors should be considered in order to make machinery which we use day in and day out, and this is essentially is a basic study and a detailed study and a research study in mechanical engineering, and which a physics students must give in for various materials with the study so that the engineers can use. Thank you.